Hello everyone and welcome to the coronavirus edition of the 11th exercise from our signal theory class. In this exercise we will practice linearization, but before we get to linearization we will take a look whether we can judge linearity of some systems. On the lecture I gave you formal definition of linearity and time invariance, and I showed you how we can judge linearity formally based on its definition. But I also showed you that there is this list of operations which create linear systems, and if I can identify that the system is built with these operations, unless there is some problem with initial conditions, I can say that the system is linear. So let's try to use this and let's check linearity of some systems. First, a system described by this differential equation. What do I have here? This is multiplication by a constant. A constant is just a special case of a function of time, and multiplication by a function of time is a linear operation, so this multiplication by a constant is a linear operation. Here I have addition of these signals, and addition of signals is a linear operation, so this addition can create a linear system. Here again I have a multiplication by a constant, that is a linear operation. Here I have derivative is a linear operation. Again, addition of signals, multiplication by constants, two derivatives, that is still a linear operation, multiplication by a constant, and that's it. So all of these operations are linear, so this equation can describe a linear system. I need to check the initial conditions, and I see that the initial conditions are 0, so I can say that the system is linear. Also, you can see that this differential equation does not change in time. These constants are just constants, they do not change in time, therefore the system does not change in time, thus it is time invariant. This is a little bit of intuitive view on the time invariance. I will show you the formal examination of time invariance, but at this point let's just do it intuitively. The next case, this differential equation is the same as this differential equation, except I have replaced this constant by this function of time. Regarding the linearity, all of these operations are linear. This is multiplication by a function of time, which is a linear operation, and I have 0 initial conditions, so the system is linear. But the change of this constant into this function of time is going to affect the time invariance. Remember, many times before we saw that the values of these coefficients set the properties of the system. And if these coefficients were constants that did not change in time, the properties of the system did not change in time, thus the system was time invariant. But if I change this constant coefficient into a function of time, now the properties of the system are going to change in time, thus the system is going to be time variant. What about a system described by this differential equation? So here I have derivative, linear operation. Here I have addition, another linear operation, multiplication by a function of time, again a linear operation, and that's about it. So based on these operations, the system can be linear, but I have to check the initial condition, which is not 0, so the system is non-linear. Regarding the time invariance, I need to examine this equation again, and here I can see that this coefficient is not a constant, this is changing in time, so this differential equation is going to be time variant. What about the system described by this differential equation? Where here I have derivative, which is a linear operation. Here I have addition, but this is an addition of a constant. Addition of two signals is a linear operation, but an addition of a constant is not a linear operation. So this system is not linear. Regarding the time invariance, nothing in this equation except of the input and the output signal is changing in time, so this system does not change its properties in time, thus it is time invariant. What about a system described by this differential equation? So the second derivative is linear, addition of signals is linear, but this cosine of a signal is not linear. So even though the initial conditions are 0, this system is going to be non-linear. What about time invariance? Well, nothing in this differential equation except the input and the output signal is changing in time, so the properties of the system described by this differential equation are not changing in time, so the system is time invariant. Now let's take a look how we can investigate time invariance formally. Here I have a differential equation of a system, and if this system is time invariant, I should be able to take the input and the output, shift them in time, and this differential equation should still hold. So let's give this a try. Let's replace x of t and y of t by these time shifted signals. I have done that here, and here I will denote this t plus delta as tau, like this and this, and when I make this substitution I will get this differential equation. And note that this differential equation is the same as this differential equation, so even when I time shift my signals, this differential equation holds, so my system is time invariant. Now what about this system? Again, I will make the substitution where I will change x of t for this time-shifted version and y of t for this time-shifted version. When I do that, I will get this. And again, I will denote t plus delta as tau. I will make this substitution, and when I make this substitution, I will get this. Here note that with this substitution, this t will become tau minus delta. So this differential equation, because of this minus delta, is different from this differential equation. So even if this differential equation holds, when I time shift the signals, I get a different differential equation, which in general is not guaranteed to hold. Therefore, the system described by this differential equation is time variant. And this is how you can examine time variance formally. On this slide, I will show you how to use linearization to deal with this circuit. In this circuit, I have a bipolar junction transistor in the common emitter configuration. This is my input voltage. It is composed from some DC bias, some constant, and some small change. This is how I will denote that DC bias, and this is how I will denote that small change. My question is, what will be the output voltage? This circuit is nonlinear because of this bipolar junction transistor. The relationship between this collector current and this base emitter voltage is given by this equation, which is obviously nonlinear. This I sub S we call the saturation current, and this V sub T we call the thermal voltage. To compute the output voltage, I first need to compute the voltage on this resistor, which is given by the current flowing through the resistor times the resistance. I have written that here. Then to get this voltage, I need to take this power supply voltage and I need to subtract the voltage on this resistor, which I have here. And that will give me my output voltage. Now when I substitute this equation into this one, I will get this relationship between the input voltage and the output voltage. Now I could take this input voltage, substitute it here, and that would give me one very long and very ugly expression for the output voltage, which I may have trouble to deal with. Or instead, I can try to linearize this circuit, which would give me approximate but potentially much simpler a relationship between the output voltage and the input voltage. To do the linearization, I will set some specific values for the saturation current, power supply voltage, thermal voltage, and the resistor R, that is this resistor. The first step in the linearization is to find the operating point. I was already given the operating point at the input, that is this DC bias at the input. What I need to find is the corresponding value of the DC bias at the output. That is, my question is, what will be the DC bias at the output when at the input I have this 0.6 volts? And that I can compute from this equation. I just need to take this V10 and substitute it here. So I need to compute this, which will give me V sub 20, and that will be that DC bias at the output. So when I take these values and substitute them here, I will get this, which is approximately equal to 4.7 volts. So my operating point will be 0.6 volts at the input and 4.7 volts at the output. Now that I have the operating point, I can proceed with the actual linearization. I can approximately express the output voltage as some DC bias, which corresponds to this operating point, plus some small change. This small change I can express as the change at the input times some constant k. This constant k I can compute as the derivative of the output voltage with respect to the input voltage, and this derivative needs to be evaluated at the operating point. I need to compute this derivative for the input voltage equal to this V sub 10. So when I take this expression for the output voltage and I compute this derivative, I will get this, which is equal to this, and this I need to evaluate at that operating point. For this V1 I need to substitute V sub 10, and also I need to substitute these values for these constants. When I do that, I will get this, which is approximately equal to 202. So this is the value of k, which I can substitute here, and here I can also substitute this delta V sub 1, which is this, and I can substitute this DC bias at the output, which is this. When I do the substitutions, I will get that the output voltage is approximately equal to this, which I can simplify to this. So this is approximate but a very simple expression for the output voltage. I can clearly read that at the output I will have some constant, some DC bias, and this cosine. Also, I can read that this circuit is actually an amplifier. I have fed it a cosine with amplitude of 10 millivolts, and I got a cosine with amplitude of 2 volts. In addition, I can see that this circuit is an inverting amplifier. You can see that here I have positive sign, but at the output I have negative sign. So this is how you can use linearization to find the output of a nonlinear system. There is one more thing worth mentioning here. Note that it is this k which sets the amplification of this circuit. This k is this value which multiplies the cosine at the input. And this k is given by this expression, which I can affect by changing the value of this V1 at the operating point. So by changing the value of the input voltage at the operating point, by changing this value, I can achieve different values of k and different amplification of this circuit. Obviously, this is going to be important when you design this type of amplifier, so we often use this type of circuit to set that operating point at the input. We use this voltage divider, which will create some DC value here, and that will set the amplification of this amplifier, and it will even set the DC value at the output. To make this work, we also use this blocking capacitor, which will prevent any DC value of a source connected here from affecting the DC value created by this voltage divider. For the same purpose, we use this blocking capacitor at the output. Oftentimes we are not interested in this DC value at the output, so this blocking capacitor will block that DC value and only AC current will pass through. So this is the principle of setting the operating point of a bipolar junction transistor in the common emitter configuration. Even though if you build this in real life, you would find that this still has some unpleasant temperature dependence. So in real life, we add some operating point stabilizing circuitry into this part of the amplifier circuit. On this slide, I will do a linearization very similar to the one which I did on the previous slide, but here I will do it on a completely abstract level. So my system, my output is given as some nonlinear function of the input. Specifically, I will use this nonlinear function. And I'm also given the operating point at the input, which is this number. So first I need to finish the operating point. I need to find what is the operating point at the output, which I will find by substituting this in here, which gives me this, which is equal to 4. So my operating point will be 2 at the input and 4 at the output. Now that I know the operating point, I can proceed with the actual linearization. So I'm linearizing this function, and to reduce clutter, I have dropped these arguments of time. Now, this function, that is this output, I can approximate using the Taylor series. So in the Taylor series, I will have the value of this function f at the operating point, which is this x0, plus the derivative of function f at the operating point, this value x0, times the deviation of the value x from the operating point. This is equal to the operating point at the output, this y sub 0, and the derivative of this function is 2x. And I need to evaluate this at the operating point when x is equal to x0. And I can substitute x sub 0 here, which will give me this. Here I can take this term and put it to the left-hand side, which will give me this. And here I can denote this difference between the output and the operating point as delta y, and also I can substitute the specific value for this operating point at the input, which will give me this equation. And this equation is approximate but a linear relationship between some small change at the input and some small change at the output. In fact, this equation corresponds to a description of a linear time invariant system. So if I'm given the input to this system, I can take it, subtract the value of the operating point at the input. That will give me that small change at the input, which I can substitute into this equation, and this equation will give me what is the small change at the output, to which I can add the value of the operating point at the output, and that will give me the output of my system. So this is the linearization of this system at this operating point. On this slide, I will show you a very simple example of linearization in the state space. For this example, I will use pendulum, which is very easy to imagine. Here I will denote the angle of the pendulum as phi, the mass of the pendulum will be m, and these are the forces acting on the pendulum. On the previous lectures and exercises, I showed you that the angular acceleration of the pendulum can be described by this expression, and this expression can be simplified into this one. Also, the derivative of the angular velocity of the pendulum is equal to the acceleration, and this equation will give you the first state equation, which based on the angle and angular velocity of the pendulum will give you the change of the first state variable, which is the angular velocity of the pendulum. Also, the derivative of the angle of the pendulum is equal to angular velocity, and this equation will be your second state equation, where based on the state of the pendulum I will get the change of the second state variable. Now, to perform the linearization, I first need to find the operating point. For the operating point, I will search for a state of the system where the system can remain steady and the system does not have a tendency to run away from that point. In the close vicinity of such a point, the system can perform small signal operation. Mathematically, I'm looking for the values of the state variables for which the derivative of the state variables are 0. So I'm looking for the values of the state variables for which this equation is 0 and this equation is 0. That is, this equation is 0 and this equation is 0. And from this second equation, I immediately see that the value of my first state variable at the operating point is 0. I can take this, put it into my first state equation, which will make this term to go away, and what I will be left with is just this term, which is supposed to be equal to 0. And that will happen when this angle, my second state variable, is also equal to 0. Therefore, from here I can pick the operating point at the state where my angle is equal to 0 and the angular velocity of the pendulum is equal to 0. And now that I have the operating point, I can proceed with the actual linearization. I will start with the linearization of this first state equation. Using the Tyler series, I can approximate this equation in this form. I need to take derivative of this function f1, that is this function, this first state equation, with respect to the angular velocity at the operating point, and I need to take derivative of this function f1 with respect to the angle of the pendulum at the operating point. When I take the derivative of this function f1 with respect to angular velocity, that is when I take derivative of this with respect to the angular velocity, I will get this. And when I take derivative of this function with respect to this angle, I will get this. And now I will need to evaluate these derivatives at the operating point. That is, I need to substitute these values for the state variables. In this case, I have just a constant, so there is nothing to substitute. I just copied a constant. In this case, I need to substitute this value for the angle, and cosine of 0 will be 1, so I will be left with this. And this is the linearization of this first state equation. Now the second state equation, this is done in a similar fashion. I need to take derivatives of this equation with respect to the angular velocity and the angle. So when I take derivative of this equation with respect to the angular velocity, I will get 1, and when I take derivative of this equation with respect to the angle, I will get 0. So at the end, I will be left with this. And this combined with this is the linearization of this second state equation. And you can see that this is pretty much the same as this, because this already is a linear equation. The only difference is that this is an equation for the actual values and this is equation for the changes with respect to the operating point. So when I put together this linearization and this linearization, I will get this linearized state space model of the pendulum. Formally, I should also include these equations which connect the actual values of the state variables with those small changes with respect to the operating point. But in this case, the operating point is at 0, so these values and these values are the same. So this was a very simple example of linearization of a system where I had only state equations and I did not have any output equation. On this slide, I have a slightly more complex example of linearization of a state space representation. In this case, I have two state equations and one output equation. To set the operating point, I am given that the value of the operating point at the input is this. To finish the search for the operating point, I also need to find the values of the state variables and the output for the operating point. The values of the state variables I need to find as values for which the derivatives of the state variables are 0. That is, I need to find values of the state variables which, when I substitute here, these equations will give me zeros. Now, these equations I have here, and I have already substituted these values into those equations. Now in this second state equation, for this u0, I can substitute this number 2, which will give me this, and this is supposed to be equal to 0. So from here I can say that at the operating point my second state variable needs to be -4. Now I can take this and substitute it into my first state equation, which will give me this. And this is supposed to be equal to 0, so from here I can get that at the operating point my first state variable needs to be equal to 2. Now I can take this value, and this value and substitute them into my output equation. That will give me this, so at the operating point my output will be minus 16. So these will be all the values that give me my operating point. Now that I have the operating point, I can proceed with the actual linearization. The linearization of the first state equation I can find in this form. Here, to reduce clutter, I have dropped all of these indices of time. So what am I supposed to do? I'm supposed to take derivative of function f1 with respect to x1. That is, I'm supposed to take derivative of this function with respect to x1. That will give me this. Then I need to take derivative of f1 with respect to x2. That is derivative of this with respect to x2. That will give me this. And last, I'm supposed to take derivative of f1 with respect to the input u. Derivative of this with respect to u. And that will give me this. Next, I need to evaluate these derivatives at the operating point. That is, I need to take these values and substitute them here. So here I need to substitute this value, which is the value of the first state variable at the operating point, and that will give me this. These two guys are just constants, so there is just nothing to substitute, and I can just copy them. Finally, I will get this, and this is the linearization of the first state equation. The linearization of the second state equation I can find in this form. So I need to take derivative of f2 with respect to x1, that is derivative of this function with respect to x1. I don't even have x1 here, so that will be 0. Then I need to take derivative with respect to x2, so derivative of this with respect to x2, that will be 1, and derivative with respect to u, so derivative of this with respect to u, and that will be 2. Next, I need to evaluate this at the operating point. All of these derivatives are just constants, so I just copy them, and I will get this linearization of the second state equation. Of course, this already was linear, so I'm going to end up with the same equation, except here I have it for the values of the individual functions, and here I have it for small changes around the operating point. Last, I'm going to linearize the output equation. So the linearization I can find in this form, and first I need to take this derivative. I need to take derivative of this with respect to x1, and that will be this. Then I need to take this derivative of this with respect to x2, and that will be this. And last, I need to take this derivative, that is derivative of this with respect to u, which will give me this. Now I need to evaluate these derivatives at the operating point. So I will be substituting this. And when I substitute this and this, here I will get this. And when I substitute this and this, here I will get this. And last, when I substitute this and this, here I will get this. And the final result will be the linearization of this output equation. To summarize my result, I have taken these equations and I have written them in the matrix form here. So this is the linearization of this nonlinear system for those small deviations from the operating point. And to this linearized model, I should also add the relationship between those small changes and the actual values of the signals. When I have the input and I subtract the value of the input at the operating point, that is when I do this, I will get that small change at the input. I can take this, substitute it here, and find what is the small change at the output. To that, I can add the value of the output at the operating point. That is, I can do this, which will give me the actual value of the signal at the output, at least approximately. If I want to get the values of the state variables, or to be more precise, the approximation of the values of the state variables, I need to take those small changes of state variables and add the values of the state variables at the operating point. That is, I need to compute this to get the approximation of the state variables. So this is how you can perform linearization of a non-linear state space description.